On the last slide, I ended on lab connections and talked about how I make solutions. And I'll continue with this idea of dilutions. You've seen me do this with stock solutions. They come concentrated, like hydrochloric acid is 12 molar. And I don't want you working with something that strong. So what I'll do is I'll do the math and figure out how much in volume is needed of the HCl for the molarity that we desire, and I add that into the volumetric flask with the water so that I can dilute the concentration and get the desired molarity that we're looking for. The moles of solute equals the moles before and after because I've put those solutes into that flask. That has not changed. The only thing that has changed is the amount of solvent, the amount of water I put in there. So the moles of solute stays the same. So for instance, a dilution lab, this is showing the orange juice, and you put the can of orange juice in there and then you add water to it. You still have that can's worth of orange juice in there. It's just spread out a little bit further. And on our chart, this is the formula V1M1 equals V2M2. We will use this quite a bit, especially as we go through acids and bases. Another way of looking at this is called mass percent. Mass percent basically is part over whole like we've done before. It tells us what percentage of solute solvent I have. So you see this on isopropyl alcohol bottles in the store where it has 70% isopropyl alcohol versus 90% isopropyl alcohol. 90% has 90% alcohol and compared to water. So it's a concentration if you want to think about it that way. Mole fraction is symbolized by chi or an X, the ratio of the number of moles of a given component to the number of moles of solution. So moles of A over total moles in the solution. We don't use this so much. I'm just laying this as a foundation idea for you. Then there's molality. We normally deal with molarity, moles per liter, but molality is the same concept. It's simply moles of solute over a mass of solvent in kilograms. It also describes the solution. It also tells us how strong it is. Normality is symbolized with a capital N. It's defined as the number of equivalents per liter of solution. Equivalence is defined as a type of reaction that's taking place in the solution. We deal with this usually when we talk about acids and bases. So 1 mole would tell us how many hydrogen atoms we have in there compared to everything else. We could also deal with normality when we're talking about redox reaction, which is reducing oxidation reactions, which is also what batteries run off of, which are redox reactions. So another vocab word. Now, we can dissolve things faster by agitating it, heating it, and crushing it. We've been through this before. Pressure has nothing to do with dissolving solids faster. Okay? It's always crush it, agitate, heat it. Now, one thing we don't think about per se when we talk about solutions is you can dissolve a gas into a solution, like what you do with sodas. Sodas are gases dissolved in solution, carbon dioxide in the solution. And it's just a little thought there as how we make soda pop. Henry's law. Henry's law relates to the concentration of a gas, usually per gases, and K is a constant and P is the pressure. It is the most accurate for dilution of solutions of gases that do not dissociate or react with the solvent. So these gases have to have no interaction with what they're dissolving into, so like carbon dioxide. Solubility graphs. You are expected to be able to interpret any type of graphs, and this is basically a solubility graph. It tells us how soluble salts are in relationship to temperature and concentration. And basically you're reading and finding out how soluble it is based on temperature. They all differ based on their chemical composition. Vapor pressure of a liquid is the equilibrium pressure of a vapor above its liquid. Okay? And that's a lot of verbiage, but if you've felt this before, if you take isopropyl alcohol and you rub it on your hand, what happens eventually? You feel that cooling effect. That's vapor pressure. Okay, it's the pressure resulting from that alcohol evaporating off. Okay, so Raoult's law, we won't be using it. I'm just pointing out this is where we would use Raoult's law on vapor pressure to figure out what our pressure is based on the vapor we're working off of. Colligative properties are properties of solutions that depends on the number of molecules and not on their individual properties, okay, such as the size or the mass of the molecules. So freezing point, boiling point, osmotic pressure, and vapor pressure are all colligative properties. Now, this makes sense because if we look at freezing point depression, as I add items into my solution, that takes even more energy to drop it down to freezing point. So we didn't really have much of a winter this year, but when you have a winter and you have potential freezing ice coming along, you can salt the surface, and that salting lowers the freezing point and prevents the ice from forming on the bridges. We can see the vice versa with boiling point depression, and we can raise that boiling point to prevent it from bowling out too fast. If you drive a car, you benefit from this because your radiator uses radiator fluid instead of just running off of water, and because of that, you can run your engine longer distances and at higher ranges because the antifreeze is keeping it from bowling. Please also note the graph here where it shows solid, liquid, and gas. Where those three combine together, that's called a triple point. That is terminology you are expected to know. And the point above where it just disappears is called your critical point.